Hi, the purpose of this particular exercise is to show you how to do a complete truss analysis, including finding the internal forces in a truss. This is very important for a project, and I wanted to do this. This is my first trial at using a video capture software, so bear with me. By the way, this is Arun Srinivasa, and I hope that this particular exercise will benefit you. So what we're going to do is a two-step deal. So we are going to start with a very simple truss, then I'll show you with a much more complicated truss in example number 2. So let me start with example number 1. So let me start. Um, what we're trying to do is to find internal forces in a truss. So I'm going to start by drawing a simple truss, and it looks like so. There is the truss. You can see that my handwriting is not that great, but bear with me. That's a pin joint. There is a roller here. Okay. And what we're going to do is we're going to apply a 12 kilopound force downwards at this point and a 10 kilopound force horizontally at this point. Let us label the points. This is A, that's B, that's C, and this is a pin, and this is a roller. So what is our task? To find the forces in the bars AB, AC, and BC. So how the heck are we going to do it? Well, our first step is to draw a free body diagram of the whole truss and find the forces at A and B. This is our usual external reaction force problem. So I'm going to draw the free body diagram now. So here's the bar. Here's the 12K force. Here's the 10K force. This is a pin joint. So there are two forces here. AY pointing up, AX pointing sideways, and this is a roller. So there's a single force BY pointing up. And this is the joint A, this is the joint B, and that's the joint C. And remember, never forget to draw the coordinate axis, and they begin along this bar and they go this way. This direction is the X direction, this is the Y direction. Oh, by the way, I forgot to give you some distances. So from here to here, it's 4 feet. From here to here, the height of this truss is 3 feet. And this distance from here to here is another 3 feet. So this is 4, that's 3, and that's 3. So I have drawn the reaction forces. This angle is 45 degrees. And it should not be too hard for you to find this angle, because this width is 4, the the horizontal distance is 4, the vertical distance is 3, so the slant distance, this must be 5 feet because of the right triangle. So it's pretty easy for us to find the angle. So the next step for us is to find the reaction forces. And we go with our usual technique of drawing a little table. Whoops, the figure went away. So I'm going to draw this in the next page right around here. And our table looks like this. Here is my point A, here's my point B, here's my point C. Here is the x coordinate, here is the y coordinate, here is fx, here is fy, and then here is the moment equals xfy minus yfx. So the coordinate of A is 0, x coordinate is 0, y coordinate is 0, fx was ax, fy was ay, and the moment is 0. Then the coordinates for B, if you want to go look at it back, it's 7 units along the x-axis and 0 units along the y-axis. So this is 7, that is 0, ax, so there is no bx, there is only a by. So turns out to be x times by x times by is 7 by. Then at point C, the x coordinate happens to be 4 feet. This is in feet, that's in feet, that is in kip, that's kip, and this is in feet kips. Really strange unit, but that's what we get. So that's 4 units along the x-axis, 3 units along the y-axis. Fx is minus is 10 kips, Fy is minus 12 kips. So xfy minus yfx is minus 12 fours or 48. And then minus yfx gives me another minus 30. So now we are ready to set sum of all the forces in the x direction equal to 0. So it goes like that, equal to 0. That gives me, let's see, ax plus 10 equal to 0. That's equation number 1. Sum of all the forces, whoops, I drew this arrow wrong. I'm going to erase it and I'm going to redraw it. Sum of all the forces in the y direction equal to 0 gives me what? Let's see, ay plus by minus 12 equal to 0. That's equation number 2. And then sum of all the moments or torques, that symbol with the arrow means that it is going counterclockwise is positive. Sum of all the moments equal to 0 gives me 7 by minus 78 equal to 0. So solve 3 and get by is 11.14 K. So substitute into 4. So we substitute it into 2 and get ay equal to 0.857 K. and then AX minus 10 kips. This takes care of our first thing. We found the reaction forces. Now that we have the reaction forces, so once we find the reaction forces, we can then look at each joint in turn and find the forces. This sounds a lot more hard than it seems, so I'm going to start, and you will see that with our systematic procedure, it's not all that hard to do. It just takes a little bit of doing. Let's make sure that all our calculations are correct. Yeah, everything is fine. So I'm going to redraw this free body diagram so that you can see what it looks like. So my initial free body diagram looked like this. So now I know this force, AY equal to 0.857, BY equals 11.14, AX equal to minus 10. So notice I left it as minus 10. We can switch the direction of the arrow around in a second, but for now we will keep it as it is. That's the force at the top and the force sideways. And as usual, this is A, that's B, that's C. What we are trying to do is to figure out the forces along the bars AC, AB, and BC. So for that, we first have to draw the free body diagram of the pin A. The trick for that, for drawing these free body diagrams, is to mark a little circle around the pin. So I'm going to mark a little circle. Once I've drawn the little circle, I'm going to draw the free body diagram to look exactly the same as the circles, in the sense that I'm going to draw the bar AC and I'm going to mark a force FAC. What it means is that the force F goes along the bar A to C, and then the force that goes along the bar A to B. So let me write that as FAB. And the two external forces, 0.857 K, and now minus 10 going to the right is the same as 10 going to the left. So I am going to draw this vector this way. I'm going to mark it as 10 kips. Notice the fact that because it was a negative, I changed the direction of the force. Okay, so now I know what this is, and now I am ready to find this angle. This angle theta I obtained from theta is given by tan inverse of this height is 3 feet, this length is 4 feet, so tan inverse of 3 over 4, which is 36.86 degrees. So that's 36.86 degrees. Now this is a simple problem of the equilibrium of a point under a bunch of forces. So as usual, I'm going to list all the forces. So the forces on this body are FAB at 0 degrees to the x-axis. Remember, the x and y-axis pointed this way. The x-axis was like this, y-axis was like that. So FAB was at 0 degrees because it's along the x-axis. FAC is at 36.86 degrees. And then the 10 kips force, 10 kip at 180 degrees. And then the 0.857 kip at 90 degrees. Couple of things to notice. First item is note that the 857 kip force is at 90 degrees because it is pointing upwards. The second item to note is that we always draw the bar forces FAC and FAB as if they are pulling at the pin. The arrows point away from the pin A and or along the bars. This is very important since it will prevent us, from making sign errors. I will not say this over and over again. I will not write this over and over again, but I'll say this for a few times so that you are sure of this. So now that I have listed the forces, it is pretty easy to say that for pin A to be in equilibrium, we need all the forces to sum to 0. So we set summation of the forces in the x direction equal to 0 gives us FAB cos 0 plus FAC cos 36.86 plus 10 cos 180 degrees plus 0.857 cos 90 degrees equal to 0. Summation of all the forces in the y direction set equal to 0 gives me FAB sine 0 degrees plus FAC sine 36.86 degrees plus 10 sine 180 degrees plus 0.857 sine 90 degrees must be equal to 0. Note that if we list the forces counterclockwise from the x-axis, the x forces, x components will always have cosines and the y components will always have signs. So we now have two equations for the two unknowns. The first equation becomes FAB plus 0.8 FAC. 0.8 comes from cos 36.86 plus, minus 10 plus 0 equal to 0. The second equation gives 0.6 FAC. FAB sin 0 is 0 plus 0.6 FAC plus 0.857 equal to 0. So those are easy to solve. You can just solve the second one and then use it in the first. When you do that, you will get, so 2 gives me FAC equals minus 1.428. That means FAB must be equal to 11.14. Sometimes I will not complete the word kips because it's kind of tricky, but so be careful because I'm a little bit sloppy on that, so I hope that's okay. Now the point which I have to make is, notice that we now have the forces. So let me recap. We first found for the whole truss, we found the reaction forces AY, AX and BY. Then we took one of these things, redrew the free body diagram for just that one pin, and we found that FAC was minus 1.428 K and FAB was 11.14 K. What this means is that the force FAB is positive. Positive means that the bar is pulling at the pin. In this case, the magnet is pulling at the ball. So this is a pulling force and this is a pushing force. Negative forces mean that the arrow is the other way and it's pushing hard. The technical names for these two things is, pulling is called tension, pushing is called compression. For our purpose, with the ball and magnet system, you can push the magnet into the ball as hard as you want and nothing will happen. So just to illustrate that, here is the ball, here is the magnet. You can shove the magnet against the ball as hard as you want, nothing happens. But if you try to separate the ball from the magnet by pulling at it, there is a max pulling force of about 1.4 pounds. So if your pulling force in the ball and magnet system, there's a maximum pulling force. So we are always interested in those forces that pull. Okay, so coming back to this picture, we have finished solving for what happens along this bar. We finished solving for what happens along this bar. What's the next step? Well, I still have to find out what's happening along that bar. So what I do is I go to the next joint. The next joint from A is the joint C. I could go either for B or C. It doesn't matter. I am going to head for C for now because I want to show you a different joint. It doesn't matter what you choose. The core idea is that at any particular joint that you choose, there should not be more than 2 bars whose forces are unknown. So it doesn't mean anything for right now, but I'll show you in a second where you have to make such a choice. So in any case, now I have to go to joint C. I will draw the free body diagram at joint C. So let me rewrite it because the new page, joint C. So remember, our overall truss looks like that. This was AY was 0.857 kips, BY was 11.14 kips, and AX was this way, 10 kips. This force is 12 kips, and this force is 10 kips. This point is A, this point is B, this point is C. Sorry. Whoops. I gotta get rid of this. Go back up here and call this point C. And then go back up here. Get rid of this. Call this point B. We already know that the tensile force along this bar is 11.14. And the compression force along that bar is how much? Minus 1.428. So I'm going to draw the free body diagram at C, and just for reference purpose, there is A and there is C. This is FAC. There's a force that goes this way, that is FBC. Then there is 12 kips. There is 10 kips. Now at point A, remember this was 0.857 kips and this was 10 kips and this was minus 1.428. Notice that I have drawn the free body diagram for that joint here, and notice that the main thing is this FAC, its arrow is pointing the opposite way. This I want to refer to, I just want you to remember Newton's third law. So this is due to a fairly complex deal, but the bottom line is that we are applying Newton's third law here, and it turns out that Newton's third law says for every action on one body, there is an equal and opposite reaction. Now this creates lots of confusion for us, so let me be very specific and say that there is a reaction force which is equal in magnitude and opposite in direction. This is very important. So notice that the magnitude of this is still minus 1.428. So equal in magnitude but opposite in direction. Can you see that the vector is pointing in the opposite direction? Now we are ready to solve for what happens at point C. So as usual, I'm going to list the forces. So there is a 10 kips at 0 degrees, 12 kips at 270 degrees. Why is that 270 degrees? Because the force is pointing downwards. Then FBC. I hope it's obvious to you that because this height is 3 feet and that height is 3 feet, this angle has to be 45 degrees. If not, you can do that by trigonometry and find out. So FBC, whoops, is at, let's see now, it's 270 plus 45, it is 315 degrees. And then FAC, FAC is minus 1.428 at, let's see now, it's 270, let's see, what is the angle here? It's, sorry, it's 180 plus 36.86. 36.86 was this angle. So just to make sure you understand, this angle is 36.86. So I'm going to move that all the way down. And so this angle is 36.86. So this angle is 180 plus 36.86. So it's at 180 plus 36.86 will be 216.86. This is the tricky part. Drawing the free body diagram and listing these forces is the tricky part. The remaining part is absolutely straightforward. There's no amazing thing to it. The main thing to notice when you draw the free body diagram is, one, make sure that all the bar forces point away from the joint. Away from the joint. Two, that we copy, if we already know the magnitude of the forces, we have to use the same magnitude. By pointing the bar forces always away from the joint, you are automatically taking care of the fact that the directions are flipped, like here and here. Notice that in both cases, the arrow is pointing away from the joint. So it's not at all a problem. We don't have to worry about Newton's third law. You don't have to make any special effort to maintain it as long as you do item 1. So make sure that you use same magnitude even if the value is negative. So if it is negative 1.14428, I just copied on negative 1.428. Now I just sum all the forces in the x direction, and I will get 10 cos 0 plus 12 cos 270 plus FBC cos 315 minus 1.428 cos 216.86 equal to 0. This will immediately give me FBC. If I do the other one, I will get 10 sine 0 degrees plus 12 sine 270 degrees plus FBC sine 135 degrees minus 1.428 sine 216 degrees equal to 0. So if you solve for FBC, you should get minus 15.75. Minus 15.75 degrees. Sorry, minus 15.75 kips. Now you might look at it and say, hey, wait a minute. There are two equations for the same value of FBC. Which one should I solve? Actually, both equations should give you the same value. If they don't, you have made a mistake in calculations. So now that we have done this, let's see where we are. Our original truss, 12 kips, 10 kips. It turns out to be 10 kips here. 0.857 kips. This side was 11.14 kips. The force along this bar is 11.14 kips, and this is pulling, and it's called tension, so we're going to write it as P. This one is minus 1.428 kips, or it is written as plus 1.428 kips. Compression, this symbol automatically means that the value is negative, and then in this case it is 15.75 kips. Compression means that this bar is pushing at the balls at the either end, so it's pushing at this ball and this ball. This bar is pulling at these two things. So pulling forces are called tension, pushing forces are called compression, and we now have all the forces inside all the bars. So if you think of the ball and magnet system, what it means is that the ball C, which is at the top, is being pushed by the two bars, the two bars AC and BC. The ball at A is being pushed by the bar AC and pulled by the bar AB, and the other reaction forces. The point B is being pushed by the bar BC and pulled by the bar AB. All of this we could calculate by a simple procedure. The first step, so let me recap, draw the free body diagram of everything. So let me quickly recap. Step 1, draw FTD of whole truss. Step 2, find reactions, find external reactions. By summation of forces and moments, summation of forces and summation of moments. Then step 3, draw free body diagram of each pin sum all the forces, set them equal to 0, and hence calculate internal forces. If the internal force is negative, then it is called compression. If the internal force is positive, it's called tension. This whole calculation is worked in a PowerPoint slide that goes with this particular presentation, that has all the calculations without any of my talking. So if you want to quickly verify what's going on, you can also look at that. There it's better typeset, here it's all written, but I hope you get an idea of how this works. Stay tuned for the next example that's going to come very shortly. Thanks. Bye.